How's it going, guys? Today I want to go over how to control a tunable LED with PWM and analog input. We're going to be using a Bridgelux LED. This is what we're going to be looking at. Had so much coffee this morning, and as soon as I start the video, this little asshole starts crawling around and making a bunch of noise. Anyway, you can see the divisions on here, the orange and yellow different sections on there. That is the warm and the cool portion of the LEDs. I think the cool portion is 5000K and the warm portion is 2700K. So it goes from about a cool white to a pretty warm white. So usually you control an LED with pulse width modulation, and I'm not going to cover much about how that works because I counted up, there are literally 2 bazillion videos about it on YouTube. So if you don't know how pulse width modulation works, pause this video, Google PWM LED, and you'll get a short video just explaining how it works. So the issue with our LED is it basically has 2 LEDs built into it. Seriously, he hasn't made any noise until I hit the record button. Anyway, so it basically has 2 LEDs in it, a cool and a warm. The cool is, like I said, 5000, the warm is 2700, and what we need to do is figure out how to control both of those LEDs in a manner that is predictable and we know what color temperature we're outputting. So depending on how much of each LED you have powered, it's going to be a different amount of color coming from each LED, and that changes the equivalent color of the entire module, this doodad. So on the data sheet, let's see here. Okay, so this is the data sheet for the LED that I have. It's the Bridgelux Vesta Series Tunable White Gen 2 18mm. And it is 2700 to 5000. So that's the one I have. I don't have the 6500. Here it is. This is what I was looking for. So we have this handy little chart right here, the one on the left, and that tells us what color temperature the LED is going to be putting out equivalent depending on how much current is going to the warm LED portion and the cool LED portion. So right here we have the current of the warm white, the 2700, and the current of the cool white, the 5000. And if you have complete cool white on and no warm white, that's going to give you a color temperature of 5000. So that makes sense. The more power you have going to cool, the cooler your overall temperature is going to be, and it's going to be, in this case, 100% cool white. It's going to be whatever the color of your cool LED portion is. So 5000. And this is a ratio, it's not a percentage, or it's basically the same thing as a percentage, but in decimal form. So you turn up the warm white a little bit and your cool white goes down. I'm going to talk more about that later because the cool white actually doesn't have to decrease. The ratio just has to be 0.2 to 0.8. So right here, that's going to get you to about 4450. It's a fairly straight line. It's a tiny bit curved, but it's about 4500 right here if you have warm white on a little bit, but it's still mostly cool white. You go all the way down to, say, half and half. That's going to be about, what's that look like, 3700 equivalent color temperature. You keep going. That's going to be if you have 0.6 warm white, so now you have more power going to your warm white than your cool white portion of the LED. That's going to be closer to 35, and then all the way to where all the power is going to your warm white LED portion and none of it's going to your cool white. And that's going to be 2700 because that's the warm white LED. So what I did is I kind of changed, I didn't take this as a straight line, just 5000 to 2700 linearly. Let's see, let's open this here, my OneNote. If you see any projects over here that you want me to make a video about, comment and let me know. Here it is. So I marked down what I thought was pretty close to it, like right here. It looks like it's right on 4000, but it's a little under it. So I just put 3990. That looked like smack dab in the middle, so 3500. That's a little above 3125. I was probably a little more precise than I should have been, but I felt like it was going to be a little closer than if I just, you know, made it a straight line. So basically I put them into Excel at 5000, 4425, 3990 based on what I put down here. So it's not a straight line. You can kind of see it's bent a little bit, kind of like a convex or concave curve. So it's not totally straight, and I put the analog input values right here that you're going to get from your potentiometer. And you only need one potentiometer because, you know, whatever your warm value is on one side of the potentiometer, the cool value is just going to be your maximum analog reading minus that. So if your warm value is 40, your cool value is going to be 1020 or 1023 minus 40, so 980 or 983. I just kind of rounded it for simplicity. And then the ratio is just the total over whatever color you're getting, so your warm ratio. Obviously, if you're doing 100% cool and 0 warm, your warm ratio is 0. Down at 50-50, they're both about the same. That gives you your temperature, your color temperature of your LED right here. It goes down from 5000 to 2700, depending on the analog input of the warm side. I'm doing everything based on warm, and cool would just be the inverse. So, and I have an Excel spreadsheet right here. This is actually what the Excel spreadsheet looked like. And here I did a best fit line, and this is the formula of the best fit line. So if you have the value of your warm analog input, you can just plug that into that formula, and it's going to have an R squared, which basically just means how good your best fit line is, of 0.997, and that's really good. That means it's super close. The closer it is to 1, the better. I would have been happy if it was at least 0.95. Below that, I would have wanted to double check and look at some things about how I read the data points off of this data sheet. And then here is the color temperature right here based on your warm value. So warm value at 0, color temperature is going to be 5000, because that means all of the power is going to your cool LED portion. And as you increase the warm ratio, which means the more power you give to the warm portion of the LED, it gets warmer and warmer. You end up all the way down at 2700. And the portion of the spreadsheet right here, I just kind of did it a little more complicated than I probably should have, but since each one of these spots was a different slope, because I took the data points at each ratio instead of just assuming it's a straight line, I got this. So that's why I needed to do a different portion for each slope, and then I just summed it all up. If you have any questions, leave a comment. I can do a more in-depth video and walk through the whole process of how I did this if you want to. If it's a question about just how PWM works, like I said, there's a bazillion other videos about it. But if you've used PWM to control an LED before, this should be within your wheelhouse. You should be able to at least catch on most of this stuff. The more astute of you may have caught on to the fact that if you want, let's say 50-50 color temperature, which is going to be somewhere around, like, what did we say, 3900? If you want something closer to the middle, you're going to give each portion of the LED the same amount of power, 50-50, right? So that puts you right in the middle here. 0.5 warm, 0.5 cool, and your duty cycle is 100. Because depending on your analog input value of the potentiometer, the inverse is going to make up for the rest and give you a total of 1023. It's going to give you 100% duty cycle. But it's going to give you 100% duty cycle total, because obviously you can't give more power to your LED than 100%. But what's interesting about this is there are two portions of the LED. Each of them can be powered separately. So you have PWM going to the warm, and you have PWM going to the cool. Now, since the color temperature is dependent on the ratio, not like total power or anything, if you send a 50% duty cycle to both warm and cool, that's a 1-to-1 ratio, or a 0.5 if you're doing it out of total power. That's also the same as 60% 60%, or 80% 80%, or 100% 100%. So if you have, if you want to turn your LED up to maximum brightness and get a color temperature right in the middle, it's going to be 50-50. Both sides of your LED are only getting 50% duty cycle based on this model here. Now, if you want to maximize the brightness, you want to make sure you're putting out as much brightness as possible while maintaining that ratio, and you're still getting a consistent color temperature. What you can do is this right here. If your warm ratio is less than 0.5, that means there's less than 50% of your color is coming from the warm, which means you're on the cooler side. You can keep your duty cycle for the cool portion of the LED at 100%, and you can get that ratio by just simply dropping the warm from the cool, and you'll get that same ratio as if you were adjusting both of them. And your equivalent duty cycle will be much higher, which means you're getting more brightness. Now, this is just the duty cycle of warm plus the duty cycle of cool right here. But that also introduces inconsistency in your brightness. So if you have it at 100% brightness and you say, I want the color smack dab in the middle, you're going to be giving 100% duty cycle to both portions of the LED. Now, you keep your brightness maximum, but you turn your color temperature up, so you're getting cooler. That keeps the cool side of the LED at 100% duty cycle, but it only drops down the warm portion. So that decreases your equivalent duty cycle, because the only way to adjust the ratio if you're keeping your cool side at 100% is to decrease the warm side. And so there's no way to keep your equivalent duty cycle at 200 because you have to decrease the warm portion, and you can't increase the cool beyond 100%. So there's two different models here. You can either keep your brightness consistent, or you can optimize the brightness, and I don't know why it's scrolling weird like that, but you can optimize the brightness, and it'll be a little inconsistent when you change color temperatures. So in this circumstance, what I would do is change the color temperature first. So like, okay, that's what I need, and then adjust the brightness. Because once you get your color temperature, you can move the brightness down or up or however you want. It won't affect it. So that is how to control a tunable LED. So in the next video, I'm going to show you how I set up the Arduino code. We're going to look at both the brightness optimized version, and we're going to see how to make sure we get as much brightness out of the LED across whatever temperature we want as possible. And then we're going to look at a simpler program that is just a straight ratio change, and it keeps the equivalent duty cycle at 100% instead of giving you that boost in the middle where you're just pumping out as much brightness as possible. Anyway, I hope that was informative, especially for anyone that's wanting to control, you know, a tunable LED or any other similar application. Be sure to be kind to someone today. World could definitely use it. So be nice to someone, do a good deed, try to make the world a better place, and till next time, deuces. It's kind of specific, I realize that. This isn't probably going to be one of my most watched videos, but I actually haven't seen anything. I haven't really looked that hard, but I haven't seen anything out there about an application just like this. I don't think a lot of people are probably doing it, so for those of you that did learn something, drop me a comment, let me know. I'd love to hear what you're working on. I would love to make video, like a more in-depth video. Not that this wasn't in-depth already, but you know, if you want to see how I made the spreadsheet and everything, that'd be fun. I mean, I'm an engineer, so I like making spreadsheets. What can I tell you? What can I say? Fallout boy. Fallout. Vault dude. Vault boy? Vault dude? I think it's Vault boy. My code for my regular job is probably done. That's got a different kind of flavor right after having coffee. Got a different lens. Ooh. Ew. Don't want it to be that close to my face. Oh.